And the final paper in this session is going to be presented by Jaehoon Jung. He's a system software engineer at Moreh. And the topic of his presentation will be DeepUM, tensor migration, and prefetching in unified memory.
Hello, I'm Jaehoon Jung, a researcher in Moreh, which develops AI infrastructure. And today I will introduce DeepUM. This work has been done when I was a PhD student in Seoul National University and advised by Professor Jaejin Lee. The current trend in deep learning requires deeper models, larger batch size, and larger dataset size. Therefore, it is a common practice to train the model from scratch with lots of GPUs led by big tech companies. Then the end user fine-tunes the model with a relatively small system. The problem is that the current state-of-the-art models are so big that even fine-tuning is hard to be performed with a small system, especially with a single GPU. Many solutions have been proposed to solve the problem. Today, we will focus on memory swapping techniques. Previous approaches in memory swapping are divided into two categories. One uses CUDA unified memory with page prefetching, and the other uses pure GPU memory with swapping in and out memory objects. Here, CUDA-UM is a memory space that can be accessed by both the CPUs and the GPUs in a single address space. It exploits page fault mechanism. Therefore, pages are automatically migrated on demand. It also enables the GPU memory over subscription, which allows using a memory space larger than the GPU memory capacity. Previous approaches have not popularly used UM for DNN due to its page fault handling overhead. On the other hand, approaches that use non-UM memory suffer GPU memory fragmentation issues. Moreover, many previous approaches require programmers to modify their code. Here, we suggest DeepUM, which supports training DNNs that exceeds a single GPU memory by exploiting CUDA-UM. It is based on PyTorch and no user Python code modification is required. DeepUM exploits correlation prefetching specialized to DNN. It also exploits two optimization techniques to minimize the GPU page fault handling time. Now I will explain how DeepUM works. DeepUM consists of DeepUM runtime and driver. PyTorch runs on top of the DeepUM runtime. DeepUM runtime manages an execution ID table that holds history of the kernel launches and contains each kernel's name and the hash value of arguments. It also passes CUDA APIs to the CUDA runtime. Let's look at an example. When PyTorch calls CUDA kernel launch API, the DeepUM runtime first looks up the execution ID table. Then it gives an execution ID. Same execution ID is given when kernel name and arguments are all the same. After that, it includes the CUDA callback function to the CUDA runtime. CUDA callback function passes the execution ID to the DeepUM driver through the Linux IO control command. Then the DeepUM runtime passes CUDA kernel launch command to the CUDA runtime. Finally, the CUDA runtime executes the commands. DeepUM driver handles GPU faults and prefetch pages by exploiting correlation prefetching. Let's look at the correlation prefetching in detail before we deep dive into the DeepUM driver. Traditional correlation prefetching is one method of cache line prefetching. It records the cache miss addresses that are correlated in correlation table. The figure below shows a snapshot of the correlation table when miss sequence is A, B, and C. When miss for A occurs again, it updates the correlation table and prefetches all addresses that are correlated to entry A. We bring correlation prefetching to the DeepUM because page fault mechanism monitors all faulty memory accesses, and kernel execution patterns and their memory access patterns are mostly fixed and repeated. Unlike the original correlation prefetching, there are two types of correlation tables in DeepUM: execution ID correlation table and UM block correlation table. While execution ID correlation table records history of execution IDs, UM block correlation table records history of faulted UM blocks. Here, UM block is a group of maximum 512 contiguous pages and a unit of management by the NVIDIA driver. In addition, there exists only one execution ID table, while there exists a block correlation table for each execution ID. Let's see what happens when a GPU page fault occurs and how correlation prefetching works. First, when a page fault occurs, the fault handling thread reads the fault buffer. Fault buffer is a hardware in the NVIDIA GPU that accumulates the information of faulted accesses. Second, it passes the information of faulted accesses to the other threads. Third, correlator thread updates correlation tables based on the fault information. Meanwhile, the prefetching thread looks up the correlation tables and calculate the block address for prefetching with the faulted block address. Then it executes prefetch commands to the prefetch queue. The migration thread handles commands from the first queue first. It migrates the faulted block to the GPU. When the fault queue is empty, it handles commands from the prefetch queue. From now on, I will explain optimization techniques used in DeepUM. Page eviction occurs when the driver fails to allocate GPU memory space for migrating faulted pages. In the figure, the page eviction logic lies on the critical path of the GPU page fault handling routines. To minimize the GPU page fault handling time, the DeepUM driver pre-evicts GPU pages when no free GPU memory space is left. We also use different page eviction policy. The DeepUM driver evicts pages that are least recently migrated and pages that are not expected to be accessed soon. We can get information from the correlation tables. The second optimization technique is related to the PyTorch GPU memory allocator. PyTorch has its own GPU memory allocator, and GPU memory objects in PyTorch are freed only when there is no more GPU memory space. Otherwise, they are just marked as inactive. In fact, the data in inactive GPU memory objects are useless. When pages in inactive memory object are selected as eviction victims, unnecessary memory traffic occurs between the CPU and the GPU. It also occupies unnecessary CPU memory space. To solve the problem, we add a few lines of code to the PyTorch GPU memory allocator to tell the DeepUM driver when a memory object is marked as inactive. When pages in the inactive memory object are selected as eviction victim, we simply invalidate them from the GPU memory. For evaluation, we use Tesla V100 GPUs, and we use 6 DNN models from various sources and with various datasets. This figure compares the speed up of LMS and DeepUM. LMS is an open source project developed by IBM. We select the batch sizes close to the maximum possible batch size of LMS and measure the speed up of training throughput over UM. The green bars show the result of UM without prefetching. LMS gray bar shows the performance of the LMS. Some numbers of LMS are missing because they fail to run the models due to the out-of-memory errors. LMS mode yellow bar is our modified version of LMS to periodically free inactive memory objects in PyTorch GPU memory allocator. By cleaning up cache memory objects periodically, we can reduce the occurrence of out-of-memory errors caused by memory fragmentation. However, LMS mode still fails to run some batch sizes due to out-of-memory errors. IDEA black bar shows the upper bounds of speedups. To get the upper bounds, we measure the execution times without GPU memory oversubscription and scale them up with the batch size. However, we do not have IDEA number for GPT-2 X large because the original PyTorch fails to run even with batch size 1. On average, DeepUM shows the best performance. DeepUM is 3 times faster than UM and 1.1 times faster than LMS. This table shows the maximum possible batch size of LMS and DeepUM. The numbers indicate that DeepUM suffers fewer memory fragmentation issues and has a higher chance of running large DNN models. This figure compares the speedup of DeepUM and other 5 previous approaches. These 5 approaches are based on TensorFlow or other frameworks and are mostly closed source. However, Ran et al. Implement these approaches in TensorFlow and measure the speed up over UM. Thus, we take the number and compare them with the speed up of DeepUM over UM. On average, DeepUM shows comparable performance to Sentinel and faster than other previous approaches. Previous approaches except Sentinel manage data at the DNN layer or tensor level. This implies that all data accessed in a layer or a tensor are moved together. The performance difference comes from the more fine-grained data movement of DeepUM with accurate prediction through the correlation tables. In the meantime, Sentinel exploits page-level runtime profiling similar to the DeepUM. However, it requires TensorFlow code modification and Linux kernel change. Moreover, it requires user code modification to identify when to start end profiling and identify each DNN layer. This is less transparent to the user. DeepUM allows a much larger batch size than all other previous approaches too. For more experiments and detailed analysis, please read the full paper. To conclude, DeepUM allows GPU memory of subscription for DNNs by exploiting CUDA-UM and using CPU memory as a backing store. It is easy to use, and we introduced a new correlation prefetching technique specialized to DNN workload, and two optimization technique to minimize the GPU page fault handling time. The evaluation result shows that our approach is effective and can handle larger memory requirements than other previous approaches. We are planning to extend DeepUM to support GPU clusters with other various parallelization techniques. Thank you.